Okay, so this next part is just the same ideas, and we're just going to dig a little bit deeper into this. So we're going to look at this from a little bit more conceptual perspective, and you may or may not follow this, and it is a kind of a deeper way of looking at it, but it's just another perspective. So it's really just a slightly different perspective on the derivative and the antiderivative, and we're just going to essentially establish that some function, in this case f of x, this function here, that line, is actually a derivative function. Okay, we're going to start this by kind of looking at this as an area. Okay, so we start at a here. This is some arbitrary starting point. I could have put a here. I can put a here. It doesn't really matter where we start a. And we're going to say that the area function, which we'll call a of x, so that's my area function a of x, that's going to be the area from some arbitrary starting point a, and where it stops is x. And whatever the you get for the area, that's our area function. Okay, so we could make a table of values, x, a of x, and if it stops at 0, it's going to be 0 area. If it stops at 1, it's going to have area 5. So we're essentially saying that the where x stops is going to give us different areas, and we're going to call that a function. Okay, that's our area function, and it's what we also call the integral, right? So that area is our integral. So we want to establish that this, in fact, the blue line is in fact the derivative of this area function. Okay, well, how do we do that? Well, if we take a look at our point here, right, we can say that this little bar here, that little bar represents a small change in area. Okay, so that's going to be a real small, that's basically a small change in area. So I'm going to say that that little red bar is change in a of x. And that change in a of x essentially, and there's a little bit of error in there, but essentially that change in a of x is going to be the f of x, or the height of the graph, times the width here, which is dx. In this case, it's been kind of labeled as h, but we see it as dx. Okay, so those, we can establish that. Well, if that's really truly the case, then, right, we can say that, well, if that little nudge, little bit of change is the same as that small area change is calculated by using f times dx, I can just algebraically rearrange this and say this. So the change in y, the change in my original area function, which I'm going to call d as well, so I'm going to call that dA, the change in the area function over the change in x must be the blue line f of x. Well, that is the derivative of the area function. The derivative of the area function must be the f of x. So that line there, that must be a derivative function. It's the derivative of this area function in here. And we can establish that algebraically, we can establish that conceptually as well. And so that's the idea here. Basically, we're saying that this small change in area is equal to f of x times h, right? They're using a little bit different notation here. And that red area, we can rearrange it, rearrange this expression into change of a, and then divide it by h. Okay, there's my change of a divided by h, and if I use a limit, I'm going to get f of x. That's essentially what I'm going to do when I make the h really, really small. So that means that a prime must be f of x, or the derivative of the area function. And so we can also say that the sum of the rectangles is a difference in the antiderivative. So this is the relationship between those two. And there's this really interesting relationship between the antiderivative and the derivative function. And there's a few different ways to do it. We've kind of established this a few ways, but this is a slightly different way of looking at it, a slightly different perspective. Okay, it's a little bit harder perspective to take because we're kind of asking you to look at this area as a function as we move. Imagine this line moving. This is line x. Okay, this line x as it moves is giving us different area, and we're going to call that different area the area function, right? Okay, so that's what it's kind of something that's a little bit different perspective to take than what we've done before.